Hello to everyone and welcome to this AMETEK Land webinar. Okay, right now I'd like to introduce today's presenters. Speaking first today is Dennis Delmastro. Dennis is the Global Industry Manager for Power at AMETEK Land and has spent over 25 years in the air emissions, environmental compliance, and energy industries. His roles have included product, project, and international sales management during his time in the CEMS sector. Dennis has recently spent 6 years at the U.S. Department of Energy's National Energy Technology Laboratory, a government research and development laboratory for coal, oil, and gas. Next, we have Derek Stuart. Derek is the product manager for power at AMETEK Land with more than 25 years' experience in industrial gas measurements. He is a member of the Institute of Physics and the ASTM, contributing to several ASTM standards. As a product development specialist, he was responsible for the design of several continuous emissions monitors, including the successful Model 4500 Opacity monitor, which is used to monitor particulate matter emissions in stack gases worldwide. Please join me in welcoming Dennis and Derek to today's event. And with that, I'm going to pass things along to Dennis Delmastro to get us started. Dennis, go right ahead.
Welcome all. This is a short presentation on opacity and particulate emissions. We hope to provide some basic education about both opacity and particulate matter and their evolution over the past 30 years. With regards to opacity and particulate, some of the basic questions to begin this presentation are: what exactly are we measuring? Who needs to measure either? Why are we measuring it? And where are we measuring it? As you can see in the photo on the right, we are measuring matter on a very small scale, generally between 0.5 and 10 microns in size. The terminology for opacity and particulate is confusing for a couple of reasons. One is that opacity in the environmental world is actually a measurement technique for determining the transmission of light through a medium. However, its use over time has become synonymous to mean dust, while particulate is the actual material itself. Many different countries have written regulations around different terms, and considerable technical literature identifies combustion materials differently. Some general terms, which to a large extent are interchangeable, include opacity, smoke, dust, ash, soot, aerosols, and fumes. For this presentation, we will utilize the terms of opacity, particulate, and dust. A fundamental question is, why does any industrial combustion source need to measure its emissions anyway? It's strictly based on the need to protect the health of a nation's citizens and to protect the environment. Countless epidemiological respiratory studies have been conducted demonstrating the adverse health effects of dust. And in response to those studies, regulatory agencies have established emission limits, and emitters must demonstrate that they are in compliance with those limits. Since regulatory actions are why accounts have to measure emissions, the regulatory requirements are usually to measure either opacity on a percentage basis or PM concentration on a milligram per cubic meter basis. You might note that opacity is actually just an optical characteristic of the plume itself, while PM measures a response, which is then correlated to dust concentration. In the very earliest days of the Industrial Revolution in America, individuals began to look at smoke coming out of their chimneys and tried to make an educated guess of how efficient their boilers were operating. A scale called the Ringelmann scale was devised to assist the smoke reader with his visible emissions. The visual observer would use a card, similar to what you see on the slide, which have 5 20% segments and an increasing darker shade of gray as you move from 0 to 100% opacity. The observer would look through the top slot at the smoke coming out of the chimney and then compare it to the 0 to 100% scale and make an opacity reading. A human visual emission reader is still used at a few small industrial locations today and is characterized as Method 9 per the USA EPA. Who needs to measure opacity? Well, in general, just about every industrial source which is burning fuel has a requirement to measure opacity or PM emissions. Based on years of experience, there are about 24 industries which must monitor opacity or particulate, including coal-fired utilities, industrial boilers, electric arc furnaces, pulp mills, municipal solid waste facilities, fluidized catalytic crackers, biomass, mineral processors, glass manufacturers, sewage burners, and others. Just about any combustion source burning any fuel other than natural gas must measure opacity or particulate. Opacity definition. Technically, opacity is the attenuation of energy of an optical light source which is transmitted through the flue gas which has particulate matter entrained. It is a fraction of the light lost in crossing the stack. By definition, opacity is equal to 1 minus I over IO times 100%. I is the amount of light returning to the detector, whereas IO is the amount of original light transmitted. As you can see, opacity units are a percentage 0 to 100%. Since opacity is the amount of light attenuated, transmission is the amount of light not attenuated. Transmission is equal to 1 minus opacity. Opacity loss mechanisms. The light energy is attenuated due to particles scattering the energy, absorbing the energy, or reflecting the energy. As you likely know, the more particulate in the stack, or the longer the path length, the more light energy will be attenuated, leading to a higher value of opacity. The easiest way to realize opacity is to think about if you were in the fog and someone was shining a flashlight at you. If you were close, you would see the light easily, but if they were far away, the light would be dimmer since the fog would attenuate more of the energy. Typically, the wavelength of the light source doesn't matter much since the light, which is attenuated, is predominantly absorbed by the particles. An easy way to understand an opacity definition is, if you have no particulate in the stack, the energy received, I, is equal to the energy transmitted, IO. Therefore, your opacity is equal to 0%. On the other hand, if you have significant particulate in the stack, the energy received, I, is completely blocked or 0. Therefore, your opacity is equal to 100%. Most opacity monitors are designed to be double-pass monitors. This simply means the light beam makes one pass through the flue gas, hits a mirror called a retroreflector, and passes back through the flue gas to the signal detector, thus a double-pass system. Double-pass systems have been the standard design over the past 20 years due to several benefits, including a simpler design since there are no electronics on the retroreflector side. It's also simpler to maintain since only one technician is necessary to service the unit, and it's easier to conduct certain QA/QC checks. Though the light does pass through the flue gas twice, a mathematical formula corrects the measurement path length to a single pass value. Most opacity monitors use LEDs, light-emitting diode light sources, that are green in color and meet the ASTM D6216 design requirement that the light source must have a peak and mean spectral response between 500 and 600 nanometers. The wisdom behind this requirement was that, if you remember back to slide 5, opacity measurements were initially conducted by visual readers. The human eye has its best photopic response around 550 nanometers, which is the yellowish green section of the visible spectrum. It was determined back then that it would be best to require opacity monitors to use light sources which produced visible light whereby a human reader would see best. Other than that, there is no real good reason why the light source could not be another color. In fact, in the earliest days of opacity monitors, regular incandescent bulbs were used and were white light sources. If any of you have not seen an opacity monitor, this slide illustrates the primary parts of an opacity monitor. The primary parts include a transceiver on the left, retroreflector on the right, a purge blower for providing purge air to both sides, fail-safe shutters to provide protection to the transceiver and retroreflector in the event of a power or purge blower failure, stack electronics, and in this case auxiliary functional unit and an auxiliary power supply, an external zero device for challenging the opacity monitor to ensure it's reading correctly, and a control room unit. One of the more important auxiliary components on any opacity monitor is the purge system. The purge system is essential for several important reasons: to provide air to keep the optical surfaces clean and dust-free, to prevent internal corrosion in the system, and to provide some cooling effects to the transceiver to enhance the life of the critical electronics. Usually purge blowers range in capacity from 18 to 50 CFM and purge both sides. If you should have a stack with a significant negative pressure, for example minus 10 inches of water column, you may not need an air purge system at all. And instrument air is always a possible option, though discouraged. Since we determined earlier that an opacity monitor, to read correctly, is path length dependent, it is necessary that a new opacity monitor be calibrated for the correct path length. This is generally known as the flange-to-flange distance and is the most critical measurement to be made to ensure the opacity monitor reads correctly. This flange-to-flange distance can usually be measured easily and accurately using a laser tape measure. You should note that an incorrect flange-to-flange measurement may require the monitor to go through another costly initial calibration, so it's important that it is correct. In the earliest days of opacity monitoring, many designs were introduced to the opacity market but had subpar performance. In order to try and standardize certain requirements to ensure opacity monitors perform correctly, the US EPA initially established a performance standard called PS1 and then eventually engaged the American Society of Testing and Materials to develop a set of design and performance specifications. Manufacturers had to adhere to these specifications and requirements as well as prove that their design could meet them. These design and performance specifications were comprehensive and extensive, but eventually improved the overall performance of opacity monitors in the market. These were known as ASTM D6216 Design and Performance Specification. This slide certainly is busy, but it gives the basic design and performance specifications that opacity monitors must meet. As a continuation of the previous slide, this slide illustrates the various design and performance specifications that must be tested and met, as well as the field audit performance tests that must be met to have a certified opacity monitor. There are factory tests, which must be performed annually, quarterly, or on each monitor, while the field audit performance tests must be conducted once the new opacity monitor is installed. Once all field tests are successfully performed, then an opacity monitor is certified and the end user will receive a manufacturer's certificate of conformance, which is known as the Blue Book. As the opacity market matured, the EPA also had an interest in ensuring that manufacturers had a written quality assurance quality control program in place for their opacity monitors. The EPA subsequently released a written QA/QC requirement entitled Procedure 3, which defined the daily, quarterly, and annual QA/QC tests which need to be conducted on each opacity monitor to maintain its certified status. Ultimately, it is the end user who is responsible to ensure these tests are conducted and carried out. Both ASTM D6216 and Procedure 3 have resulted in an installed base of quality opacity monitors. As air pollution control equipment, such as baghouses and electrostatic precipitators, improved in their particulate removal efficiencies, the levels of opacity begin to drop towards the 10% opacity levels. At these levels, the particulate concentration of dust in the flue gas are low enough where opacity readings are more difficult but not impossible. Therefore, opacity monitors can actually be used to measure particulate concentrations. However, there is an absolute lower level. The relationship between opacity and PM concentrations are defined by the Beer-Lambert law. Though there is some fancy math, essentially, opacity is equal to 1 minus the exponential raised to the power of minus k times C times L, where k is a constant, C is the particulate concentration, and L is the path length. Being that there is an exponential function, it is easier to use another term called optical density since it is related to opacity. Therefore, optical density is equal to 2.303 times K times C times L. And finally, by rearranging terms, one can solve for the value of C, the dust concentration. Thus, dust concentration in milligrams per cubic meter is equal to optical density times a calculated constant K2. Now in these cases, K1 and K2 are constants which involve the particulate size, specific gravity, and specific extinction coefficients. Note, the opacity scale of 0 to 100% is equal to the optical density scale of 0 to 2. Now, to summate the differences between opacity and PM, the following table illustrates the predominant differences. Most notably, opacity is measured in percentage, while PM has measurement units of milligram per cubic meter. Opacity measures across the stack, while PM tends to be in situ. Opacity is measured off light attenuation, while PM is predominantly measured off light scattering. Opacity is a direct measurement of light attenuation, while PM has to be correlated to an isokinetic test method to provide a dust concentration reading. Now, opacity regulations are pretty old, while PM regulations are fairly new. And finally, opacity is usually the initial regulation of an emission source, which then tends to give way towards PM regulatory limits.
Okay, Dennis, thank you very much for your part of the presentation. Now, please stay with us, and we'll come back to you at the end so you and Derek can answer some questions for our attendees. Right now, I'd like to pass things along to Derek. Derek, go right ahead.
Hello, I'm Derek Stuart, Industry Product Manager for Power at AMETEK Land. I'm going to talk about measurements of particulate matter, or PM. As Dennis explained, opacity measurements give a measure of the amount of dust and smoke leaving the stack from a combustion process. A PM monitor quantifies those emissions in mass units, usually milligrams per cubic meter, but sometimes grains per dry standard cubic foot. PM monitors are used in many of the same applications as opacity monitors, but regulations in some countries or in some industries may specify one or the other. For example, all applications in Europe require PM measurements, not opacity. In the US, power generators have a choice of opacity or PM, but the cement industry must measure PM. Several measurement techniques can be used to detect the low levels of PM that are encountered in modern emissions measurements. In addition to opacity, the most common are light scattering and charge transfer. There are various implementations of charge transfer measurements, often referred to as triboelectric or electrodynamic sensors. These are very sensitive, but they can be difficult to use as they are also sensitive to parameters other than the PM concentration, things such as velocity and temperature. So these parameters have to be measured and a correction applied. The most common PM sensors employ some form of light scattering. Forward, side, and back scattering are all used. No matter which sensing technique is used, the sensor does not generally measure PM concentration directly, but it measures a parameter related to that concentration. Although an opacity monitor can be used to measure PM concentration, its sensitivity at the low end is limited. The chart shows the typical detection limit for an opacity monitor used to measure PM. As you can see, even on a large stack, it is difficult to measure PM concentrations below 1 or 2 milligrams per cubic meter. This was not a problem in the days when typical process emission limits were in the region of 50 or even 100 milligrams per cubic meter. But nowadays, emission limits can be as low as 10 milligrams per cubic meter, which is impractical with an opacity monitor. There is a lot of interesting physics related to the interaction between light and solid particles. Fortunately, you don't need to understand all of the maths to use a light scattering sensor. However, it's worth knowing about the way that particle size influences the scattering pattern. The smallest particles scatter light more or less homogeneously, with the amount of scattering inversely related to the fourth power of the wavelength. This type of scattering was first described by Lord Rayleigh, and the effect bears his name. Interestingly, it's the reason the sky is blue, because blue light has the shortest wavelength in the visible spectrum, and so it is the most strongly scattered. Larger particles scatter preferentially in the forward direction, and particles that are larger than the wavelength of light scatter most strongly in that direction. Gustav Mie derived the mathematical description of such scattering from Maxwell's equations, and the theory bears his name. This is relevant to us because most of the PM in a typical stack has a size of 1 to 3 microns, a bit bigger than the 0.6 micron wavelength of red light used in the sensor. Therefore, these particles scatter light very strongly in the forward direction. The main advantage of light scattering over opacity at low dust concentrations is that there is no signal when there is no PM present. An opacity monitor measures the difference in signal between 100% transmission and the 98% or 99% that is actually seen. That requires a very careful design and very stable electronics to work effectively. As the PM concentration goes down, we're trying to measure smaller and smaller departures from the 100% transmission condition. Conversely, with a light scattering system, all of the signal comes from the particles we are trying to measure. As we saw in the previous slide, particles scatter light in all directions, and practical PM monitors employ forward, side, or back scattering. Each method has its advantages and drawbacks. Side and back scattering monitors shine a laser into the stack and detect the light which is scattered or reflected towards a detector mounted on the outside. They share similar pros and cons. There are no optical components inside the process, so nothing is exposed directly to the hot, corrosive combustion gases. Because the unit does not penetrate into the stack, it's possible to perform a calibration audit without removing the sensor from the process. This makes life easier for the user. However, the physics of the scattering process mean that these configurations are less sensitive, and they're also more prone to changes in particle size. The geometry means that the measurement region is close to the stack wall, so it can be difficult to ensure that the measurement is representative of the bulk particles in the process. In a forward scattering configuration, the laser and electronics are mounted on a probe, part of which penetrates the stack. Near the end of the probe, the laser shines into an interaction region where it is scattered by any particles present. This scattered light is collected and measured. The forward scattering configuration has several advantages. The signal level is much higher, there is less sensitivity to particle size, and locating the measurement region further into the stack means it's easier to achieve a representative sampling location. These advantages outweigh the drawbacks in most applications. For example, a careful design of air purge will stop the stack gases from damaging the optical components. The probe does need to be removed from the stack to perform an audit, which is time-consuming, but it's generally something that has to be done every 3 months and is not unduly bothersome. Here's a more detailed view of the interaction region of the Land 4650 PM instrument. You can see the laser beam passing through the interaction region and then passing through a hole in the collection mirror before entering the beam dump. The mirror collects the scattered light and focuses it onto a light pipe, a quartz rod, which carries it back to the detector mounted outside the stack. The light pipe allows us to keep all of the electronics out of the stack, so the only things in the hot environment are passive optical components. A problem common to all opacity and in situ PM-CEMS is that they cannot distinguish dust particles from water drops. That means they cannot be used anywhere there could be condensed water present in the sample. That's not a problem in most traditional applications, but the increasing use of wet flue gas desulfurization, or wet FGD, means there are a lot more wet stacks than there used to be. In a wet FGD system, a slurry of limestone and water is sprayed into the flue gases. The lime reacts with the sulfur dioxide to form gypsum, which is a solid. The gypsum is then recovered and used to manufacture wallboard for building. The stack gases have lost most of the SO2 that is present, typically 98 or 99%, but they are now laden with condensed water drops. You can easily tell when a power plant is employing wet FGD because it has a dense, white, billowing plume of condensed water leaving the stack. There is a solution to measuring PM in wet stacks, but it is rather expensive. A heated extractive sample system takes some of the flue gases to an oven. Provided the residence time in the oven is long enough, the water drops evaporate and the hot, dry sample can be measured using a standard forward scattering sensor. Careful design is needed to ensure the PM entering and leaving the oven remains representative of the material in the stack. Unfortunately, all of the additional hardware increases the price of the PM-CEMS by a factor of 4 or so relative to an in-situ system. In most cases, a PM-CEMS measures a parameter which is related to the dust concentration rather than measuring the concentration directly. For example, the opacity or the intensity of light scattered by the dust in the stack are the measured parameters. A correlation test is the mechanism used to relate that measured parameter to the PM concentration, which is what we want to know. It's an essential part of almost every practical PM monitor regardless of the sensing technology employed. Let's look at the correlation test in a little more detail. The basis of the test is to make a series of measurements using a manual reference method and then compare the results with the output from the PM-CEMS made at the same time. The graph here shows a set of data from a Land 4500 opacity monitor. The instrument was configured to output optical density as a 4 to 20 mA signal, and this is shown on the x-axis. The reference method data are shown on the y-axis. Most standards require a spread of data for a valid correlation, so the graph includes data taken with low, medium, and high dust concentrations, with the maximum concentration up around the 90 mg per cubic meter level. Here's a schematic of the equipment used for a typical reference method measurement, such as a US EPA Method 5. It consists of a sample nozzle which points into the stack flow, a filter which is weighed before and after the test, a flow meter so we know how much gas we have sampled, and a flow regulator which allows us to adjust the sample rate. This last point is important. The velocity of the sample entering the nozzle has to be closely matched to the velocity of the flue gases. That is a condition known as isokinetic sampling. If we don't have isokinetic conditions, the dust sample entering the nozzle will not be the same as the dust in the stack. That's because the momentum of the particles means they will not follow the streamlines of the gas sample. If we sample too quickly, we will undersample heavy particles because their momentum will make them miss the sample nozzle. Conversely, sampling too slowly will increase the number of large particles in our sample. There are some important considerations for a successful correlation test. The key thing is that the sample points for both the PM-CEMS and the reference method need to be representative. That is to say, the PM concentration and size distribution has to be the same for both of them, and they also have to match those in the stack as a whole. Measurements of low dust concentrations can be very difficult. It takes a long time to accumulate a measurable amount of dust on the filter, and careful handling is needed to make sure the filters are not contaminated or damaged. There have been cases where a negative PM concentration was measured because the mass of filter paper lost in handling was greater than the mass of the particles sampled. Because it can be difficult to generate adequate medium and high-level measurements by changing the process conditions, it's sometimes necessary to spike the sample by injecting fly ash directly into the flue so that it can be measured. The main standards for the correlation test are US EPA Performance Specification 11, or PS11, and European Standard EN 13284 Part 2. As you might expect, PS11 is used in the US, and EN 13284 is used in Europe. However, they're broadly similar. The key points are that the PM-CEMS should be operated for a period before the correlation test. This is important. The test is expensive, so you need to be confident that the instrument is operating correctly before you start. A minimum of 15 data points are needed. In most cases, at least 18 measurements will be made across a range of dust concentrations and operating conditions. Recording additional data allows us to reject a few bad sample points if necessary. One difference between PS11 and EN 13284 is that the US standard recommends the use of paired sample trains, which makes it easier to detect poor precision and bias in the measurements. A least squares regression is used to fit the reference method data to the PM-CEMS measurements. In most cases, a linear regression gives a good fit, but the standards allow polynomial, exponential, and logarithmic fits. Fortunately, the statistical tools in a spreadsheet make the calculations easy. Once we have the correlation graph, the standards require statistical tests for quality of fit, so we can be sure we're not simply plotting a graph through a set of random numbers. The required values are the confidence interval, the tolerance interval, and the correlation coefficient. If the data pass all of the statistical tests, we can use the correlation data to determine the PM concentration using our PM-CEMS. Here's a worked example showing some data which passed the statistical tests. Even though there is some scatter in the data, the correlation is good. Both the confidence interval and the tolerance interval meet the requirements of PS11. Most instruments allow the curve fit parameters to be programmed into the PM-CEMS so that it displays and outputs the measurements as calibrated milligrams per cubic meter. So we can now program the slope and offset from the graph into our PM-CEMS and use it to gather real data. At AMETEK Land, we offer a range of instruments for both opacity and PM measurements. The 4500 Mark III is our flagship opacity monitor, offering excellent accuracy, stability, and reliability in a package that's easy to use and easy to service. It has a 3-year warranty, and the LED light source is guaranteed for the life of the instrument. The 4650 PM is a forward scattering laser sensor for use as a PM-CEMS. It can be calibrated in accordance with PS11 or EN 13284, and it has a minimum range of just 0 to 15 milligrams per cubic meter. For more information on these and on the full range of AMETEK Land products, please visit our website www.landinst.com. Thank you for coming to the webinar today, and Dennis and I will be happy to take questions.
Dennis and Derek, thank you so much for those great presentations. Okay, Dennis, let's get to your first question. At times I hear the word transmissometer. What is the difference between a transmissometer and an opacity monitor?
Well, in reality, they are both the same instrument. Remember, transmission plus opacity is equal to 1. When a beam of light is transmitted through a medium, some of the light is attenuated while some of it is transmitted. Transmission and opacity are complementary to each other.
Okay, Dennis, thanks for that answer. Here's another question. Can any opacity monitor use any type of light wavelength to measure opacity?
Unfortunately, no. Performance Specification 1 mandates a peak and mean spectral wavelength between 500 and 600 nanometers. This is in the visible spectrum. Essentially, UV, visible, and IR wavelength light sources could be used since the particulate really doesn't care what the wavelength is that they absorb. That being said, it is true that Moisture and CO2 in the flue gas can absorb some wavelengths of light, and therefore some of the reason why the 500 to 600 nanometer wavelength is required.
And Dennis, thanks again for that answer. Here's another question. Are there single-pass opacity monitors?
Yes, there is a laser-based system which projects a laser through the medium onto the detector on the opposing side of the stack. A laser beam itself has no real advantage over an LED light source, but a fiber optic light pipe is used to transmit light from the transceiver to the detector to conduct their zero and upscale daily calibration checks. This can be problematic when an off-stack zero must be conducted 1 out of every 3 years as required in Procedure 3.
Okay, Dennis, thank you very much once again. Here's another question. Do all opacity monitors have transceivers, retros, blowers, stack electronics, external zero devices, and control room units?
No, most opacity monitors are modular and consist of optional components. In the most simplistic configuration, one only needs a transceiver, retro, and purge blower for the system to operate. A data cable would transmit stack readings to an end user's data acquisition system.
Okay, Dennis, thank you for that answer. Now, this next attendee asks, are fail-safe shutters that necessary?
In about 5% of the cases, one may need fail-safe shutters. The reason is most stacks, for safety purposes, have a negative draft in the stack. Since this negative pressure is present, if the purge blower should fail or power outage occur, the negative stack pressure will still pull air through the transceiver and retroreflector, thus protecting the optics.
And here's another question, Dennis. I'm a bit confused over the PS1 and the ASTM D6216 design and performance specifications. Can you please explain?
PS1 was codified back in the 1980s and was referred to as 40 CFR 60 Appendix B Performance Specification 1. It established the initial design and performance specifications for opacity monitors. Thereafter, the EPA worked with ASTM on several different occasions to improve the design and performance specifications. ASTM D6216-12 was the last version, which also had an Annex A1 included, which addressed the design and performance specifications for opacity units in applications less than 10% opacity.
And thank you once again, Dennis. Here's another question. To obtain a certified opacity monitor, must the manufacturer conduct any tests?
Yes, ASTM D6216 identifies the specific tests that a manufacturer must conduct. These tests include 1 per unit tests, 2 quarterly tests, 3 annual tests, and 4 field audit tests. The purpose of the tests in 1 through 3 are to validate and certify that the opacity monitors being built meet both the design and performance tests. The field audit performance tests validate and certify that the installed monitor meets the proper performance tests.
What field tests must be conducted to certify a new opacity monitor?
There are approximately 6 tests which must be carried out on a new opacity monitor, including an optical alignment, a calibration error test, a response time test, averaging period test, zero span drift test, and a 168-hour operational test. If the opacity monitor successfully passes these tests, it is a certified opacity monitor.
And thanks once again, Dennis, for that answer. Another question for you. What is a manufacturer's certificate of conformance?
It is a comprehensive booklet issued by the manufacturer to the end user that the opacity monitor is certified. This document, also known as the Blue Book, contains the test results of the per unit, quarterly, and annual validation tests, which prove that the opacity unit met the design and performance test criteria and successfully passed the field audit tests.
And thanks again, Dennis. We have a couple more questions for you. So if any opacity monitor can measure dust concentration, why does one need a PM monitor?
True, an opacity monitor can measure dust concentration after developing a correlation curve like a PM monitor, but there are lower limits to this measurement. Once particulate in the stack is at levels which results in opacity levels falling to 10% and below, then it is more accurate to utilize a particulate monitor. Particulate monitor is a high-gain instrument, so once there is any particulate in the stack, it can render a response. A PM monitor essentially works in reverse of an opacity monitor.
Okay, Dennis, here's your last question. Can you explain optical density?
Optical density is a logarithmic measure of the amount of attenuated light, or opacity. Optical density is equal to minus log of 1 minus opacity. This equation can also be rearranged to read opacity is equal to 1 minus 10 to the negative optical density power. Optical density has a nonlinear relationship to opacity. The scales are, for opacity, it's 0 to 100%, while for optical density, it is 0 to 2.
And Dennis, thank you so much for those answers. Now, Derek, there's a lot of questions here for you as well, so let's get to those, shall we? Derek, here's your first question. What is the highest stack moisture content where I can use an opacity monitor or in situ PM-CEMS?
There's no limit to the moisture content, provided the water remains in the vapor phase. However, opacity and PM monitors cannot distinguish water drops from dust particles, so any amount of condensed water will cause problems.
And thanks, Derek, for that answer. Here's another question for you. Do I really need to use a purge air blower, or can I use a compressed air instead?
Most opacity monitors require a large amount of purge air, so it's not practical to purge them with compressed air. In general, in situ PM-CEMS require less purge air, and so compressed air can be used for these. However, it must be dry, oil-free, and particle-free. Otherwise, it will cause contamination on the optical surfaces. This will cause offsets and incorrect readings.
And thanks once again, Derek, for that answer. Here's another question. Can I use an opacity monitor in a high-temperature process? And what is the maximum temperature for an opacity monitor?
The light beam is the only part of the opacity monitor which is in contact with the process gases, so high temperatures don't generally cause a problem. At extreme temperatures, usually above 600 Celsius or 1100 Fahrenheit, the mountings may become too hot and damage the seals. The other potential problem above 1000 Celsius or 1800 Fahrenheit is radiative heating of the electronics. Both of these problems can be overcome by lengthening the mounting pipe of the instrument.
Okay, Derek, here's another question. Does ambient light affect the readings from an opacity monitor?
The Land model 4500 modulates its light source at 3 kHz, and the detection electronics only respond to signals at this frequency. That makes it insensitive to light sources such as sunlight or ordinary room lights, which are effectively DC. The ASTM D6216 standard requires an opacity monitor to remain spec when it's exposed to 900 watts per square meter of sunlight. That's the sort of solar radiation intensity you get in New York on a sunny summer's day.
Should I use a shutter to isolate the opacity monitor from the stack?
A shutter provides useful safeguards in case of purge failure. It also lets the user isolate the stack from the opacity monitor for maintenance and calibration. That's essential in positive pressure applications, but it's not normally needed in the more common situation where the stack has a negative pressure.
Okay, Derek, thanks for that answer. Here's another question. What preventative maintenance is needed on an opacity monitor?
There's very little preventative maintenance that's actually needed for an opacity monitor. You need to keep the optical surfaces clean, and you need to change the filter on the purge blower. That's pretty much it.
And thanks once again, Derek. Here's another question. Isn't President Trump going to abolish the EPA anyway?
Well, the President's budget plans do include big cuts to the EPA budget, but the Clean Air Act remains in force, and in addition, most process operators want to be good neighbours and they don't want to gain a reputation as a polluter. Environmental monitoring is going to remain important for the foreseeable future in the US, in Europe and around the world.
And Derek, this questioner would like to know, why does my opacity monitor sometimes give negative readings?
Like any measuring device, an opacity monitor has a specified uncertainty. Some of the uncertainty factors, such as lens contamination, will always give a positive offset. Other factors, like installation path length or the electronic noise, can give a positive or a negative offset. If the process opacity is only 1 or 2%, as is common nowadays, the combined negative uncertainty factors can exceed the actual stack opacity. In those cases, you will get a negative opacity measurement, even though the instrument is functioning within its spec.
Thank you very much, Derek, for that answer. We have a few more questions for you. How often do I need to recalibrate my opacity monitor?
In the United States, Procedure 3 requires annual recalibration. 2 years out of 3, this can be done on the stack using an external zero device, but every third year the monitor has to be taken down off the stack and set up in a clean laboratory at the correct path length for a true off-stack calibration. The external zero device also has to be recalibrated at that time.
Thanks very much, Derek. Here's another question. I have a metal stack which twists as it heats up. Will this cause a problem with my opacity monitor?
A well-designed opacity monitor will work correctly provided any misalignment is within specified limits. For example, the Land Model 4500 Mark III is specified to be within 1% opacity for misalignment of plus or minus 1/4 of a degree in angle. That's good enough for most applications. The only cases where I've seen severe problems are in double-walled stacks where the installer has fixed the standpipe, has fixed the opacity mount to both the inner and the outer stack. That can cause severe misalignment as the two cylinders move relative to one another. If you've got a double-walled stack, it's essential to mount the opacity to either the inner, which should be normal, or to the outer, but definitely not to both.
All right, gentlemen, those are all the questions we have time for right now. Derek Stuart and Dennis Delmastro, thanks so much for taking some time to be here with all of us today and sharing all that great information. And a special thanks to all of our audience members for being part of this webinar event. Take care and have yourselves a great day.